Okay. Hi, everyone. Today we have the privilege of hosting one of the most renowned figure in the world of theoretical physics and mathematics, Professor Edward Witten. Prof. Witten is a distinguished American and mathematical and theoretical physicist who held the position of Professor Emerit at the Institute for Advanced Study and Princeton. Professor Witten works in a range of topics, including string theory, quantum gravity, supersymmetry, quantum field theory, and their profound connection to mathematical physics. His groundbreaking contributions have not only shaped our understanding of the universe, but have also left an indelible mark on the pure mathematics. In 1990, Professor Witten achieved a milestone in the history of science by becoming the first physicist ever to be awarded a Fields Medal by the International Mathematical Union. Furthermore, he is the founder of cerebral M theory. Today we have the privilege of delving into Professor Edward Witten and Witten's incredible body of works, exploring the frontier of theoretical physics and mathematics, and gaining insight into his fascinating journey through the world of science and physics and mathematics. So let's dive into our conversation with Professor Edward Witten. We appreciate Professor Witten for graciously accepting our invitation and dedicating your valuable time. Thank you so much.
Thank you for the invitation.
Okay, let's begin by, to begin, could you tell us about your early inspiration and what led to your pursue a career in theoretical physics and mathematics?
When I was very young, I was very interested in astronomy. You might remember those. I was growing up in the 50s. Those were the days of the space race. So everybody was excited about space. And I thought I wanted to be an astronomer when I was big. But I remember being very afraid that by the time I was grown up, astronomers would have to live in space, which sounded scary. It's interesting that, 60 or so years later, space satellites are very important in astronomy, but the people who work on them live and work on the ground. Anyway, astronomy didn't become quite as dangerous as I feared. However, at the age of about 11, I was introduced to more advanced mathematics, calculus, and then I thought I was going to be a mathematician. And you could argue that that's almost what happened. But it ended up that when I was a little older, I decided to go into physics because I was fascinated by the elementary particles.
Okay. Thanks. And Mr. Witten, what prompted you shift from studying economics to pursuing a PhD in physics at Princeton University? How did this change influence your academic and research trajectory?
Well, to be honest with you, I realized that economics wasn't the best match for my personality and my skills, and that I was better trying to do math or physics. But it was to some extent, it was a random decision between math and physics because I didn't understand very well what was involved in either one.
Okay, thanks. And could you, Professor, provide insight into your doctoral dissertation titled "Some Problem and Short Distance Analysis of Gauge Theory"? What were the primary discovery or impact of this dissertation or your subsequent work in the field of theoretical physics?
Well, these were the early days of the Standard Model. So what's called asymptotic freedom of strong interactions had been discovered just a few months before I started graduate school. And it was understood that protons, neutrons, and other strongly interacting particles are apparently made out of quarks and gluons. But it's actually quite mysterious because we think that protons and neutrons are made out of quarks, but the quarks never separate. If you try to separate a quark, the energy grows indefinitely. That was a puzzle which fascinated me. It really even obsessed me as a graduate student, and I would have loved to make progress with it, but that was too difficult. And certainly at the time, I wasn't able to make progress, and even later, only a little bit of progress. And even today, you could argue that the problem isn't as well understood as we would like. Anyway, the strong interaction theory, what we call quantum chromodynamics, had been invented. And that raised a lot of deep problems, which I couldn't make progress with. But then there were easier problems that I wrote my thesis about. So in my thesis, I made a few applications of what's called asymptotic freedom of strong interactions. That's the statement that quarks interact weakly at short distances, though they interact strongly at long distances. At long distances, we don't understand what's happening. At short distances, we can calculate. The most significant calculation I did as a student, I guess, had to do with what's called deep inelastic photon-photon scattering. It's a reaction that occurs when you collide two electrons, or an electron and a positron, and you can produce a lot of strongly interacting particles as well as the electron and positron in the final state. And for a certain range of energy and momenta, you're in what's called the deep inelastic regime. And my most significant contribution as a student was to calculate what happens in that regime. By the way, at that time, the experiment wasn't really practical. It was more than 20 years, I think, before that experiment was really done with reasonable precision.
Okay, thank you, Professor. And 1990, you received the Fields Medal for your mathematical contribution to physics. Could you share some case insight from your award-winning works, such as the proof of the positive theorem, positive energy theorem and generativity, and also your interpretation of John's invariance of norms?
Well, as I told you, in my student days, the standard model of particle physics was new. And the standard model of particle physics raised a variety of new questions that physicists weren't familiar with. And it gradually became clear that topics in modern mathematics that physicists didn't know much about were helpful in understanding the standard model. This became clear through things like work on instantons and magnetic monopoles that were discovered as part of the standard model. And in the case of instantons, which played an important role in understanding how the standard model works. And gradually it became clear, first of all, that physicists had a use for mathematics we didn't know. And secondly, that physicists could sometimes have insights about mathematics that surprised the mathematicians because the physical problems led naturally to these insights. And I view my career as having been mostly a story of being at the right place at the right time to do some of that. So I made a few contributions in that direction, and I guess that was the background for the Fields Medal.
Okay, thanks, Professor. But the people want to know more about this, the development of this knot theory and its application, and what is the difference between the topology and knots theory?
Well, first of all, as understood by a physicist, as understood in everyday life, a knot is a nuisance. You have a piece of string that unfortunately is tangled and you'd like to untangle it. And that's an example of what mathematicians would call a knot. So technically, a knot is a circle embedded in three-dimensional space, but perhaps winding around in a complicated fashion. And von Jones, well, there's a long history in the 20th century of mathematicians studying knot theory and finding a deep mathematical theory. But von Jones, in about 1983, had discovered something that was called the Jones polynomial, a rather surprising invariant, technically it's called. That means a way of deciding if two knots are really different or the same. If you have two different tangled pieces of string, it's easy to see that they're both tangled, but it's very hard to determine if they're tangled in exactly the same way, meaning that keeping the ends fixed and just trying to untangle the tangles in the inside, can you smoothly deform one into the other? That's a difficult problem in everyday life. Well, usually in everyday life, what we want to know is if it can be untangled. We're not really trying to determine if two different tangles that can't be untangled are equivalent to each other. That's the problem that the mathematicians tend to pose. Anyway, von Jones discovered a surprising new way to address that kind of question. And then Jones and others discovered an amazing web of connections with theoretical physics involving originally integrable models of statistical mechanics, but then involving other things like conformal field theory. Now, Michael Tiede, the distinguished mathematician, presented to me the problem of describing in a natural way that would have the three-dimensional symmetry obvious, the Jones polynomial. Because Jones's definition and all the others, you could prove that they worked, but it wasn't obvious why they worked, what was behind it. So following Tiede's question, I did succeed in finding a physics framework that made the invariance of the Jones polynomial manifest, although it made the computability of the Jones polynomial less obvious. It took detailed arguments to show that the Jones polynomial defined the way I did was computable and equivalent to what Jones had defined. But anyway, that's what I succeeded in doing by interpreting the Jones polynomial in the context of a three-dimensional gauge theory. That means a gauge theory in a three-dimensional spacetime.
Okay, thanks. But the people talk about the multi. For example, there is Jones polynomial and also Alexander polynomial. Why we use all of these polynomials? What is the difference between?
Well, originally the Alexander polynomial was discovered maybe half a century before the Jones polynomial. In its day, it was a big advance. It was a way to decide if two tangles were equivalent. It doesn't always give you the answer, but it often does. What mathematicians of that day could understand was basically what could they understood with the Alexander polynomial. In 1983, Jones discovered a more powerful approach, the Jones polynomial. It gave a more powerful criterion to decide if two tangled pieces of string are equivalent.
Okay, thanks. Knot and knot theory are always linked with the concept of string. We know that the string theory is a theoretical framework that suggests that the fundamental building block of the universe are not particles, but teeny vibrating string. You're often referred as one of the key figures and the development of string theory. Could you provide an overview of what string theory is and its significance in our case of understand the fundamental nature of the universe?
Well, first I'd like to back up a little bit and discuss 20th century physics in general. One of the main reasons physics made so much progress in the 20th century was that a framework was discovered that's very rigid and where it's very difficult to do anything that makes sense but isn't in the right direction. That was the framework of relativistic quantum field theory. So there was quantum mechanics, Einstein discovered special relativity. Combined, they have this framework of relativistic quantum field theory. That's the most difficult physics theory to learn that we have today. There's Einstein's theory of gravity, general relativity. It's incredibly beautiful. But honestly, quantum field theory is much more difficult to understand. And it puts you on a narrow path where you're limited in what you can do. And for example, when the weak interaction part of the standard model of particle physics was discovered, experimental data was very limited, very, very limited, especially from a point of view of today. Nevertheless, from very limited experimental data, the theory was discovered because the framework didn't give you too many options. And moreover, changing the framework and still being consistent is almost impossible. So quantum field theory is almost a century old, and it's a framework where you can combine relativity and quantum mechanics. And there's almost nothing you can change in that framework that leaves it still making sense. The only generalization of the framework of quantum field theory that physicists have discovered in the last century that makes any sense even before you try to compare to nature is string theory. We don't understand string theory very well. We're still struggling with trying to understand what it means.
Kiara Nappy, or
although we don't understand it very well, we have found that string theory is a framework that generalizes the standard framework of quantum field theory, and that does make sense. It preserves the consistency with the general principles of special relativity and quantum mechanics. Now, what does it say about nature that's different from what quantum field theory says? The most important thing that it says that's different is that gravity has to exist. So physicists trying to work in the framework of quantum field theory found that gravity didn't fit into that framework. Einstein's nonlinear mathematics wasn't consistent with the requirements of quantum field theory. Instead, though we still do not deeply understand why, string theory forces gravity upon us. String theory automatically generates gravity. So the main interest in string theory, I would say, comes from two things. One, it's the only option we've discovered for how we can sensibly generalize the well-established framework of quantum field theory and to try to go beyond that. And two, we know that gravity exists. Gravity is forced upon us in this new framework and appears to be impossible in the previous framework.
Okay, thank you so much. For example, there is some, I think there is a lot of string theory. For example, we know that there is Polyakov action and non-Bigoto action. And we know there is the string theory and superstring and bosonic string. What is the difference or distinction between the bosonic string theory and the superstring theory?
Well, the bosonic string theory is a theory that almost works, but as best we understand, it's not really consistent because it's unstable. It's a theory that only has bosons. So in nature, we see two kinds of particles, bosons and fermions. And bosons are the quanta of light or the graviton. The photon, the quantum of light is a boson. The graviton, the quantum of the gravitational field is a boson. And for example, the hydrogen atom, because it has both a proton and an electron, is a boson, but the proton and the electron separately are fermions, the other kind of particle. So the bosonic string theory only has bosons, but knowing that fermions also exist in nature, physicists, the bosonic string theory was essentially invented by Veneziano in around 1968, or at least the original equations that led to the bosonic string theory were invented by Veneziano. But knowing that fermions exist, physicists Ramond, Shirk and Schwartz and others wanted to invent a string theory that would have fermions as well as bosons. I should also mention Neveu. So obviously a string theory that has both fermions and bosons is more realistic than one that only has bosons. In inventing a string theory that has fermions as well as bosons, they ended up inventing supersymmetry. Supersymmetry is the symmetry between bosons and fermions that you get in the simplest string theory construction that has both kinds of particles.
Okay, thank you. When we talk about string, the people like the general relativity and classical mechanics talk about particles. We use string and not particles.
If string theory is correct, then think about first a piano or a violin string or a guitar string. It vibrates with many different harmonics. And so there's a fundamental tone, but there also are what are called higher overtones. The beauty of music comes from the interplay of the different harmonics produced by a string or another musical instrument. A pure note is produced by a tuning fork. It sounds very harsh to the human ear. So and the beauty of music depends upon the interplay of these higher harmonics. If you have one of these strings that I study vibrating in space, it can likewise vibrate in many different shapes and forms. The different shapes and forms of the vibrations correspond to the different elementary particles. So if string theory is correct, at least in its simplest version, the different elementary particles correspond to different harmonics of one basic string. That's the way the different particles and fields are unified into one underlying theory.
Okay, thanks. For example, how we can understand the notion of mass, spin, charge, and the context of this string or string theory?
Mass, spin, and charge all come from symmetries of the string theory, but that part of it isn't new. In the 20th century, we learned that mass, spin, and charge are related to underlying symmetries. So without string theory, you have quantum field theory, and its symmetries lead to mass, spin, and charge. And that part of the story is preserved when we get to string theory. That statement is part of the statements that string theory agrees with ordinary, better established physics at long distances. So part of long distance physics is that we can define the charges. In fact, a lesson of Einstein's theory of gravity and also of the gauge theories of the standard model is that mass, spin, and charge are all best measured in terms of the behavior of fields at a big distance. So the Gauss flux integral for the charge historically and more modern versions for mass and angular momentum. And since these are long distance observables, part of the statement that string theory agrees with ordinary physics at long distances is that these charges are still defined in string theory.
Okay. Are superparticles a form of antimatter or a different category, and can they be considered as dark matter candida or anything like that?
Well,
Okay.
superparticles. Okay. Superparticles are not the same as antimatter. They have their own antimatter. So the electron has an antimatter particle, the positron. If supersymmetry is correct, at sufficiently low energies that this discussion makes sense, then the electron also has a more massive superpartner, which would have its own antiparticle in turn. So it's conceivable that a superpartner could be a dark matter candidate. But you have to bear in mind that there are many, many conceivable possibilities for dark matter.
Okay, thank you. For M theory, is a concept closely associated with your name. Can you give us an overview of M theory and its role in unifying various string theory and explaining, please, the fundamental force of nature?
By 1985 or so, physicists understood that there were 5 apparently consistent versions of superstring theory. They differed by things like whether the string is an insulator or an electrical conductor, and whether the string is only a closed loop or whether there also are open strings with ends. Anyway, there were 5 string theories that differed by conditions like that. Now, the existence of 5 string theories was a little bit of a puzzle, because if one of them describes our universe, who lives in the other 4 worlds? Why do the other 4 string theories exist? That's one of the deep questions of those days that actually was answered. It was found initially in some developments in the 80s and then more completely in the 90s that the different string theories are all equivalent to each other when you study them more closely. That there's one underlying theory that we now often call M theory, and the 5 different string theories are limiting cases that are valid under appropriate conditions.
Okay, when we talk about M theory and string theory, we talk also about extra dimension. Can you give us a more clarification about this dimension, extra dimension?
In their simplest versions, at least, string theory and M theory do require extra dimensions that are usually taken to be compactified, very small, so that in everyday life we don't see them. We effectively average over them. But part of the richness, if string theory is correct, part of the richness of the elementary particles in this framework comes from the fact that, well, I mentioned that the different particles come from different states of vibration of the string, but I didn't explain that in detail. An important part of that is that the strings can vibrate in extra dimensions, and that's important in leading to the richness of the elementary particles as we observe them.
Okay, when we talk also about M theory, we talk about everything. Could you please provide information about this theory of everything?
Well, personally, I never use the phrase theory of everything because I don't like melodramatic language. So M theory, if it's correct, is a much more comprehensive theory than we've known previously. It's not obvious why it couldn't be a theory of everything, but I personally avoid making that kind of claim.
Okay, thank you. Black holes, for example, are fascinating objects in astrophysics, and they can have application for the nature of space-time and the formation. Do people speak a lot of black holes and the creation of black holes and the Earth? Also, the relationship between the black holes and quantum information. Can you give us more information about black holes?
Well, of course, black holes are fascinating objects. Even if you're not a physicist, just reading about them in the popular literature is fascinating. The idea that a star at the end of its lifetime collapses to nothingness, a hole in space from which nothing can escape, is fascinating. And it first came out of Einstein's equations not long after those equations were written. But for decades, people didn't know whether to take it seriously.
Okay.
I'm not sure people really came to take it seriously until experimental evidence observational evidence for black holes started to appear, which I guess was in the 70s, more or less. Originally, the evidence was not very direct. People saw things in space that were so small and so heavy that anything you could think of that was so small and so heavy seemed like it would be unstable and would collapse to a black hole. So Okay, but it wasn't very direct evidence that we had a black hole. By now, though, we have rather direct evidence for black holes, both from gravitational wave observations and even from the photographs taken by the Event Horizon Telescope, it's called, the network of radio telescopes spanning the Earth and taking high-resolution pictures of the neighborhood of the black hole. So by now, we have amazingly concrete evidence that black holes do exist in space. Theoretically, though, they're quite mysterious. The idea of an object that can absorb matter but can't emit it appears to violate fundamental principles of physics, such as the idea that the Hamiltonian is Hermitian. But Stephen Hawking discovered in the 70s, and this was his greatest discovery, that at the quantum level, black holes aren't completely black. They emit radiation. A black hole emits radiation at a very low temperature that we call the Hawking temperature. Unfortunately, this is a purely theoretical insight. Although we see black holes in space, the Hawking temperature is so small that when we are observing a black hole, there are all kinds of things going on that are much bigger effects than the Hawking temperature. So in practice, we're not able to test Hawking's prediction observationally, not in any way accessible to us right now. You can speculate about the future, but in the foreseeable future, we can't test it experimentally. However, theoretically, black holes pose contradictions. As I said, before Hawking's work, there were even cruder contradictions. Hawking resolved some by showing that black holes emit as well as absorbing matter. But physicists to this day don't properly understand how black holes can be reconciled fully with quantum mechanics. The basic problem is that when Hawking says that a black hole can absorb matter and that it emits what it absorbed back as Hawking radiation. But the Hawking radiation, when we calculate it, appears to be random, whereas physical principles say it shouldn't be random, that whatever information there was in whatever fell in should be contained in whatever comes out. We don't know how to make that more concrete.
Okay, thank you. We talk also about another object like black string, black brane, and this object. What is this object, black anything?
Well, the black strings and black branes are generalizations of black holes that can exist in higher dimensions. Purely in 4 dimensions, you don't really have black strings. But in 5 dimensions, you can have a black string, and in higher dimensions, you can have black branes as well. And so, from a theoretical point of view, they are indeed part of what we grapple with in string/M theory.
Okay, we talk also about, I see some paper, quantum gravity and string theory, talk about replica wormholes and the black hole anterior and pitch curve of radiation and the semi-classical geometry. What is this name of this theory?
Well, first of all, the things you're talking about are some of the very avant-garde ideas that physicists have explored in just the last few years. So we don't understand in detail how to reconcile a black hole with quantum mechanics, but some of the general contradictions were resolved at some level a few years ago, where it was shown that, well, given some hypotheses that we think are true about duality or equivalent between gauge theory and gravity, about what we call holographic duality, given some general principles that we think are true, but of course they're speculative, some of the black hole contradictions could be resolved using replica wormholes and all those other funny things you mentioned.
Okay, thank you. Are there attempts to unify quantum mechanics and general relativity within the context of black hole?
Well, the Hawking effect is an effect where gravity and quantum mechanics work together. So trying to understand it properly, well, involves making gravity and quantum mechanics work together at a higher level than we are able to currently. So I could say the general challenge of reconciling gravity and quantum mechanics and possibly string theory is the correct solution, but we don't understand it very well. We're trying to understand it better. But if you think about a black hole, some of the contradictions, some of the problems become more explicit, more concrete.
Okay, we talk also about the concept of black holes related with the quantum extremal island. What is this extremal island and the concept of black holes?
Well, one of the ideas of physicists like Hooft and Susskind and others starting in the 90s is that, okay, there's a mystery with the black hole, which is that things fall in and we don't see how the information gets out. And a partial answer that's been proposed, it sounds a little strange at first, is that there's a sense in which the information never went in, that whatever is in a region of space can actually be described just on the boundary of that region. That's called holographic duality. And it might sound like a crazy idea, but very powerful evidence for it was discovered starting in the late 90s and continuing to the present day. The hypothesis is held up very well. So we have a lot of confidence in it, though it isn't completely proved. Now, if you had access to the complete boundary, according to the holographic hypothesis, you'd understand in principle everything about what's inside. But what if you only have access to part of the boundary? Then more contemporary developments seem to show that you can describe in what is present in part of spacetime called the entanglement wedge. And originally people thought the entanglement wedge was connected to the part of the boundary that you have access to. But some of the more modern discoveries is that the entanglement wedge can have a disconnected piece that people call an island.
Okay.
I'm sorry if I've given an answer that has more mystery than explanation or clarification. But unfortunately, the question you're asking about, which is what is the entanglement island, doesn't lend itself to a simple explanation that everybody's going to understand, unfortunately.
Do you think is our universe is a hologram, really hologram? And this is the concept of holographic principle or another?
Well, I don't know. A conservative statement is that we understand what holography means when the cosmological constant is negative, but in the real world it appears to be positive. And we don't understand what holography means with positive cosmological constant. So I don't know the answer to your question, is the world holographic? Or let me interpret your question to mean, does the world have a holographic description, the real world?
Okay.
I do not know a framework in which there could be the framework of holography that I know doesn't apply well to the real world because the sign of the cosmological constant is wrong. What will be discovered in the future, I can't tell you. But regardless of whether the real world does have a holographic description, what you and I live with in everyday life is what physicists call a bulk description. We don't see the hologram. We see the bulk of space-time, or the space at given time. And we see time marching forward, or we experience time marching forward. So there may be a holographic description, but I can't tell you who would have access to it. Not us.
Okay, no, yeah, really. Okay. I back another question about the compactification of dimension. What is this compactification and Calabi dimension and this compactification and topology of these things?
Well, if there are extra dimensions, since we don't see them in everyday life, the way out, which incidentally was suggested by Einstein in one of his papers in the 1930s, Einstein and Bergman to be precise, is that the extra dimensions should be very small so that we don't see them in everyday life. We average over them. Or to be more precise, the particles we see have wave functions spread over the extra dimensions, not localized in the extra dimensions. That's a more quantum mechanical language to explain why we don't really see them in everyday life. So we would see them indirectly because the different particles, the electron, the muon, and the tau, for example, to name three particles. So you all know about the electron, but probably only those of you who are physicists are familiar with the muon and the tau. But in nature, there are three similar particles, the electron, the muon, and the tau. So one mystery is why there are all three. So to simplify a bit, roughly, the electron, the muon, and the tau would have different wave functions in the extra dimensions. So the extra dimensions have to be compact or we would see them in everyday life. And they're part of the theory, at least in the simplest versions of the theory. And we hope they explain why the electron, the muon, and the tau all exist.
If this dimension are responsible for the vibration of this string?
Well, the strings would be vibrating in these extra dimensions. So if you wanted to calculate what the spectrum of vibrations, in other words, how the string can vibrate and what is the energy, the charge, and the spin of each type of vibration of the string, that would depend on the structure of the extra dimensions.
Okay, thank you. Many people find the concept and theoretical physics quite abstract. And how do you approach explaining complex idea to a broader audience? And what advice would you give to young scientists looking to communicate their work effectively?
Well, it can be hard to explain. It's true that the ideas in theoretical physics are a bit abstract. That's been true since at least since the early 20th century. Maybe it was true before, but by the early 20th century, people had gotten used to the ideas of Newton and Maxwell, and then the new ideas of Einstein and then of Bohr and other quantum physicists seem very abstract. And quantum field theory definitely seems rather abstract in the sense it's very heavy mathematical machinery you have to use. So as for how to explain it to a general audience, I've done my best in this interview, but I'm afraid the listeners will have to judge the extent to which I succeeded. As for advice to young physicists about explaining their work, well, that's hard to do, but try to find simple terms in which you can explain things.
Okay. Throughout your career, many people find the concept and theoretical physics is abstract. And throughout your career, you have been collaborated with numerous scientists, made a contribution to a wide range of topics. Are there any particular research collaboration or projects that stand out as a particularly memorable or impactful to you?
Well, definitely, I've had several important collaborations. I maybe have to first mention my work with my colleague at the Institute, Natty Seiberg, in 1994, where we understood the dynamics of certain supersymmetric gauge theories. And that even enabled us to say a little bit about the problem of confinement, which had why quarks don't separate, why the energy grows if you try to pull a quark out of a proton, which had obsessed me so much as a student. And also that work was a platform for a better understanding of string theory at multiple levels. So that was a highly memorable collaboration. Two of the other physicists with whom I've had memorable collaborations are my former student Qumran Vafa from Iran, and also the Italian physicist Davide Gaiotto.
Theoretical physics and mathematics have evolved significantly during your career. What's some of the most exciting development or open questions in these fields today that you find intriguing?
Well, understanding what string theory or M theory really mean, to me, is the biggest puzzle. That's what I would most like to achieve. But it appears to be out of reach in the foreseeable future. We have to find something that's a little bit more accessible. Getting a better understanding of quantum nature of black holes is actually the problem that has had the most exciting progress in the last decade, in my opinion. The progress has mostly been, well, one important voice is my colleague at the Institute, Juan Modosena, but a lot of the work has been done by younger physicists. I would not say that I've made major contributions myself, although I've been increasingly interested, and I've tried to contribute something to those developments.
Okay. As a professor emeritus, what advice would you offer to aspiring physicists and mathematicians who are just beginning their academic journey or researcher careers?
Well, try to learn all you can when you're young. That's one safe bit of advice.
Okay. Thanks. Finally, on a more personal note, what are some of your interests and hobbies outside your scientific pursuits?
Well, I play tennis. I unfortunately didn't take it up seriously until I was about 45. So Someone who learned younger would have learned better than I did. But anyway, I have fun playing tennis. I hope to be able to continue playing for as long as I can, but we'll see. It gets harder as we get older. I took up piano about 4 years ago. So I'm trying to learn piano. That's another thing I'd be doing better if I started a little bit younger. I like chess, but I don't really play chess anymore. I just watch videos about chess. I have some favorite YouTube chess channels. So I watch commentary on interesting chess games. And I've had a lifelong passion, which I'm afraid has been thoroughly unrequited, for peace in the Middle East. That's been a lifelong disappointment, not seeing more progress in that direction.
Okay. It's nice to know the interesting of the great scientist Edward Witten. It's a pleasure for me. Okay, I think this is the questions that I have. Okay, we take a few followers' questions before the finishing the live. We start by the first question. The first question, could physics or science in general change our understanding of axiom or logical principle one day in the future?
Well, we certainly might change our understanding of the fundamental principles of physics. In fact, it's clear that the principles of physics as we understand them are incomplete. So I don't know how much success we'll have in doing better, but the physics, our understanding of the axioms and principles of physics is in need of improvement, and maybe we'll have success one day. Maybe even what we're doing now is progress toward that. I'm not sure exactly how the question was intended, but something that comes to mind is whether physics could influence a rethinking of the foundations of mathematics. I'm not an expert myself on the foundations of mathematics, and I don't know whether it's possible, how plausible it is. The only thing that comes to my mind there is that mathematicians have found it very difficult to understand quantum field theory mathematically. And I do wonder sometimes if it's at all conceivable that a rethinking of the fundamentals of mathematics would help in providing a framework where quantum field theory would seem more natural. That's just a pipe dream. I have no idea what I'm talking about. I'm just making a random speculation anybody could make. But that's the best I can say. Thank you for the question.
Okay. The next question is, can you please ask Prof. Witten about the alternative theory of string theory that's a good candidate to unify quantum mechanics and general relativity?
My personal view is that there aren't any significant alternative theories. Sometimes when I'm giving a lecture, I'm asked to compare different theories. And the answer I've kind of arrived at giving is that to work successfully in physics, and this is not just in the field I work in, but in any area of science, really, to work successfully in science, you have to develop your ability to judge for yourself what proposals and which claims are serious and which ones are not. So that's part of the advice to aspiring physicists, is that you will have to develop an ability to judge for yourself which ideas to take seriously.
Okay, there is another question. The hypothesis the topology of the universe is similar to Aperture's, but how we can understand that as if the future looking back and the time and the Earth here is begin and the center of the universe.
Well,
I think.
Okay, so the question is about what's the nature in the large of the whole universe. What's what we would call the topology of the whole universe. Is it a big sphere? Is it more like a plane? Or is it a more sophisticated thing called a hypertorus? I don't know. And there's a problem with being able to find out, which is that one of the fundamental principles of relativity is that signals don't travel faster than light. And that puts a limit on how far we can see, and potentially on how far we can ever see, given that the expansion of the universe is now accelerating. That potentially puts a limit to how far we could ever see, even if you wait far into the future. So it's entirely possible that the topology of the universe is something unknowable to us.
Okay, the next question. Does the professor think that we are close to major achievements on mathematics or physics?
Well, of course, major achievements in different areas of mathematics happen all the time. But I'm going to, as a physicist, interpret the question in a very extreme way. There are also in different areas of physics, there are important achievements that happen all the time. But I'm going to assume that the questioner is asking me, are we close to a breakthrough where we get a new understanding of the most fundamental principles of physics? I'm going to assume that that might be what the questioner has in mind. So that, as a physicist, that's the highest standard I could put for what the question could mean. And unfortunately, I don't know. I think we've made very significant advances in the last 40 or 50 years in understanding what are likely to be ingredients in new physics. But to really put it in a form where we could say definitively, these are the new principles and this is the new framework in which we should understand physics, it's impossible to know if we're close or far to that.
Okay, can you comment on this comment? I assume that the cosmic emission mass gap and Young means be the same manifestation to usage of everything but from different physical interaction.
So first of all, thank you for the question. So even though there are similar words used, the ideas are rather different. The mass gap in Yang-Mills theory is a kind of mathematical question about how the theory behaves. It's also an observational question because both real experiments and computer experiments seem to show that Yang-Mills theory has a mass gap. But as theorists, we don't understand how to calculate it. So I mentioned that as a student, I was obsessed with the problem of quark confinement. That's a close cousin of this problem of the mass gap. So it's an unsolved problem in theoretical physics to this day. But I want to stress it's a problem about understanding the solutions of the equations that are known. Yang-Mills theory has known equations, but we have trouble solving them. We think we know, both from real experiments and computer simulations, that the solution has a mass gap, but we don't know how to solve the equations well enough to prove that. So that's the nature of that problem. The cosmic missing mass is something else. We can try to figure out how much mass there is in the universe by looking at how fast the universe is expanding. Or we can simply look at all the mass we see. We look at all the mass in stars. We take all the mass that we're able to see. Some mass is missing because the mass that we see in stars is less than the mass that we infer from gravity. So there's missing mass, or as people often call it, dark matter. That's an experimental phenomenon. We don't know what equations describe it. It could be anything. It could be supersymmetric particles, as I was asking one of the questions during the interview, but there are all kinds of other things it could be. I sort of have a hypothesis I like that's called fuzzy dark matter, which I wrote a paper on a few years ago with some colleagues. But observationally, dark matter could be anything. It's just a mystery what it is.
Okay, this question. Okay.
I hope we'll learn the answer to that mystery observationally, but there's no guarantee because depending on what it is, affects how hard it is to discover what it is. There are things dark matter could be that would not be accessible observationally in any foreseeable way, unfortunately. There are many things we could observe, and there are ongoing searches for some of them. So we hope to find out what it is, but life doesn't come with promises. As I also remarked when I was asked, I didn't, not in those words, but that's the fact that life doesn't come with promises is something I could have said when asked about the next real breakthrough.
Okay. This question, what the relation between ransom and quantum field theory with reality?
I'm not sure what's ransom.
No, this is quantum field theory with reality. I think this is
quantum field theory is the framework where physicists, starting around 1930, succeeded in combining quantum mechanics with Einstein's special relativity. Not general relativity that includes gravity, but special relativity, which says what happens when speeds are close to light. Quantum field theory is an extremely successful theory observationally. It's the framework in which we have the standard model of particle physics. It's extremely well tested. So quantum field theory makes contact with reality in all the experiments we do in our particle physics labs, and lots of other experiments, including low energy experiments, measuring magnetic moment of the electron and all kinds of other things, atomic physics, molecular physics. So quantum field theory makes contact with reality left and right. It's our most powerful, most successful theory.
Okay, the last question is, what is the current status for the research and the string theory?
Well, the current status is a little hard to summarize. There's exciting work going on in many different areas. And my biggest problem as a researcher is not knowing which of numerous interesting papers to try to read and understand. The result, unfortunately, is that I can't keep up on everything I would like to keep up on. As I mentioned, the direction where I think the most interesting progress is currently being made has to do with quantum properties of black holes. So I'm trying to keep up at least with those developments. And even there, I have a lot of trouble because too many things are happening. So the current research status of research in string theory is that it's multifaceted, many-fingered, happening in many directions.
Okay, thank you, Professor Edward Witten, for joining us today and sharing your insight. We're excited to explore the fascinating world of theoretical physics and mathematics with you. Thank you, Professor, so much for your time, and welcome to Morocco.
Well, thank you so much, and I do hope to come to Morocco in person at some point in the not-too-distant future.
Okay, thanks so much. Thank you.
Thanks for the invitation. Be well. Be well, everybody.
Have a